Well, there's a few news links that you might like. This is apparently the biggest fraud ever in California. As part of the inmates in prison have somehow figured out how to apply for stimulus payments, having unemployment and having something to do with the COVID stimulus, and stole $1 billion. And they're just beginning to track down how to stop it. So that's interesting. See what comes of it. Been several corruption cases like this punished insiders. This one doesn't appear to be an insider job, but we know that the Trump family and his friends embezzled a whole lot of this money too up in Washington, but locally it was apparently the convicts that stole it. This tends to happen when you just hand out such large amounts of money without any real oversight. Anyway, we'll see what comes of that. So Emily Murphy finally approved the transition to Biden, and she had been painted as a Trump loyalist and a villain in the liberal media that I listen to, but it says here, the thing about her is she didn't dare approve it, and when she finally decided that she had to approve it, she prepared to get fired. And that's why she had been applying for other jobs and stuff. She assumed that Trump would fire her as soon as she approved the transition, which is quite reasonable to imagine. And she told him and got no answer and went ahead and did it. And he came up a half hour later saying, oh, it was my idea, I told her to do it, which is of course a lie, like almost everything he says. But she apparently, he had figured out that there was no point. Apparently he was very impressed by Rudy Giuliani's makeup smearing, because Trump is very, very concerned with how things look on TV. And when he saw Rudy Giuliani babbling nonsense with his makeup awry on TV, then he lost faith in Giuliani and realized he's going to lose, which is very much on brand for Trump. He fires people all the time if they don't look the way he wants them to look on TV. Anyway, so that pretty much that's as close to a concession as we'll ever get, and it's all over but the shouting and the lying and the television deals at this point. So Binance is one of the cryptocurrency exchanges, and it is kicking all the United States users off of it. And this has in the past indicated, it's in a foreign country, and this in the past has indicated that they're about to be shut down by legal action. And they prefer to get all the United States people out of there so they don't have international lawsuits to deal with. So this is probably yet another cryptocurrency exchange that's going to be shut down by legal action. Coinbase is the main United States cryptocurrency exchange, and they are very carefully legal. They obey all sorts of laws, even egregious laws like this one. This is going to cut their business a lot. If you buy stocks, you typically do it on margin. This is what caused the crash in 1929, but it remains a very popular way to invest. I want to buy $10,000 worth of stuff, but I only have 1,000, so I just borrow the rest, buy more stock than I can afford, hoping it will go up, and then I'll make more money. And they've been doing that all along. But the latest government regulation appears to say that it's illegal to do this with cryptocurrency. So Coinbase is going to obey that and end this highly popular, highly lucrative trade starting tomorrow. Because Coinbase has been letting the government jerk them around like crazy all along because they're trying to survive government action. All the other cryptocurrency exchanges have pretty much been shut down because they were determined to be illegal. And Coinbase always works real hard to obey the laws, no matter how burdensome or foolish they are. So, but they got in trouble with this one. They've been sending out these letters to everybody. See, if you own cryptocurrency and the cryptocurrency changes its value, which it does wildly, then they need to report that to the IRS. But the IRS has never made up their mind. What is this stuff? Is it cash? Is it capital gains? What is it? So they tried to figure out what form to put it on, and they decided to use the 1099-K, and the 1099-K is being interpreted by the IRS as realized gains. So people whose cryptocurrency went up in value are receiving tax bills for incredible amounts, like $127,000, because the cryptocurrency went up in value, but they didn't yet sell the cryptocurrency. And in fact, I saw a tweet saying that on the forums, people are discovering they cannot in fact sell their Coinbase cryptocurrency and get back to dollars right now. People are trying to do it. So if that persists, that's going to be another big problem. But that's what tends to happen with people in cryptocurrency. They tend to get stuck in cryptocurrency because the exchanges keep being shut down. Anyway, so this is apparently the wrong letter, but it's very unclear what the right letter would be. And this is why John McAfee is in prison for tax fraud having to do with cryptocurrency. If you do make money in cryptocurrency, it is in fact very difficult to decide how to pay your taxes. So you really need to get a good tax attorney and expect a lot of changes in your tax bills. This was, I remember seeing this in the news before. This was one of the things during the Mueller investigation. There were communications between Russian bank and a Trump organization, and an independent researcher found this stuff and reported it. And so people are suing, trying to find them and punish them. The Alpha Bank was to sue them for embarrassing the bank, showing that they were in contact with the Russians. And a reporter who actually knew, a reporter wrote an article about it, and Indiana University professor had contact with one of these researchers and made their findings public. So they were suing this professor, demanding that they reveal the identity of this person who found the communication. And they have succeeded in squashing that subpoena, which is not common. I've reported some vulnerabilities myself, and anybody that does this discovers that they do give you a lot of legal grief for doing that. Anyway, so in this case, they managed to continue keeping the identity of the researcher that found the communication secret, which is sort of a blow for independent security researchers. The Office of Management and Budget, this is something came out before. This is the detail. 88% of all employees in the federal government are now moving into a new category called Schedule F, which means the president can't fire them. The president has been very frustrated at his inability to fire, for example, Anthony Fauci and other people working in the government. He would like to be able to fire anybody that says anything he doesn't like, and he can't do that. Quite a few of them have sort of civil service protection, so they are ending that. And people are quite troubled by this. Of course, it will make the government more like communist Russia, where you have a political officer next to you at every moment. You can be fired for making a politically incorrect statement, which is certainly the way Trump wants it. But that's not the way the Democrats want it. So we may see some change in this. By the way, we've got a guest speaker coming up from the Office of Management and Budget. If you go down here, this person is from FireEye, and after that comes some people, one from the FBI and one from the Office of Management and Budget. So in a couple of weeks, we'll have a guest lecture from them, and you can ask them questions about this or any other topic with the federal government. Anyway, so Facebook had another bit of their scandals have leaked out. Facebook is extremely criticized for the weird way in which they punish people for saying blatantly illegal, crazy things like lies about coronavirus, lies about government decisions. And they're very unclear. And now it's turned out that they have a special list of important political figures who will not be punished for anything they say, 100,000 people. And that list is now leaking. And the fact that that list exists is leaking. And this is yet another embarrassment for Facebook. It has been very clear all along that the Facebook rules are inconsistent, unclear, unfairly enforced. And, you know, on the other hand, the legal regulations of what Facebook is legally required to remove are also completely unclear. So that's why, you know, I've said before, I often have sympathy for Zuckerberg. Zuckerberg went before Congress and they said, why did you censor this and you didn't censor that? And he said, well, why don't you guys pass a law and tell me what to censor? If you'll just make up your mind, I'll do that. I'm just trying to figure it out, but you know, I don't know what I'm supposed to censor or what I'm not supposed to censor. And of course, our government can't decide what they want either. So it is difficult to condemn Facebook too much for doing the wrong thing when you haven't decided what the right thing is. So this is a big topic now. Biden has been signaling quite a lot that he doesn't want to focus on punishing Trump, which is certainly in general a good idea, because when the incoming administration jails the outgoing administration, you're turning into a very corrupt, scary society. But on the other hand, Trump certainly committed an incredible number of crimes, many of which are not federal but state crimes. And so anyway, there are people arguing about whether you should punish Trump and what you're going to do about it. Yeah, and if I was Biden, I would just say, I'm not going to have anything to do with it personally. I'm going to let the legal departments just do whatever they want, and I'll recuse myself from it. And you know, inevitably, I think the end result is Trump can afford expensive lawyers, and he will more or less get away with it, but he will be sort of harassed and waste a lot of time and money dealing with all this. But we will see what comes of it all. I think I'll skip that one. And you know, this is the big divide that seems to be splitting America is primarily on education. The right-wingers are the people without a college education, and the left-wingers are the ones with a college education, largely, certainly not completely. And that is a very interesting issue. And I must say, personally, I think the most logical solution to this is Andrew Yang's. You have to give people a universal basic income so they're not so desperate. Oh, state crimes, Chad is asking. Oh, the state crimes are financial. He did a whole lot of state crimes in New York. He ran a fake charity and just pocketed the money. He ran a fake college and just stole the money. He ran a military veterans charity. He also took the election campaign funds and just spent it. He also defrauded his taxes, state and federal. So most of his crimes are federal, but a lot of them are also in the state of New York. And that's important because he can pardon himself, or he could quit and have Pence pardon him for the federal stuff, but that would not apply to state crimes. So in a way, it may not be up to Biden anyway. Even if Biden didn't want to do it, it would be up to the prosecutor in New York whether to prosecute him for the state crimes. So, but certainly most people regard it as a bad thing for the country when you start prosecuting your outgoing president. It does create the appearance of corruption in your society that we might want to avoid. We will see what happens. That's why, in general, they've never done it in the past. Didn't do it to Nixon, didn't do it to Carter. They mostly just try to move on without focusing on the outgoing leader, because they figure that, I figure half the people in the country appear to love Trump. They will probably be really, really mad if you prosecute him. And is it really worth it? But anyway, I think that's where Biden is thinking, but we'll see what comes of it all. Anyway, so we're here today. We're going to talk about data encoding. So let me go here. All right, so these are ways to express data. And the point is, you can just stick data in programs in the obvious way, and then they're easy to find with the techniques we've been using. And so if you want to hide the strings in your data, you can hide things like the domain for the command and control center, and disguise, you make your malware look like it doesn't have any suspicious strings in it. And often what is done is you use obfuscation. This is, right, and this is the point. Normally, if you're trying to really protect data from unauthorized exposure, you have to use a real encryption routine like AES or RSA or something. But in malware, they often use these old-fashioned, ridiculous, simple things like the Cipher or just base64 encoding for the same reason a lot of people use these simple things in the source code of web pages, because you're not really trying to stop it from a serious professional attack. You're trying to make it so people can't easily detect the strings or easily just copy and paste the code. So you often use a very simple obfuscation technique. It's called obfuscation. It's kind of a sliding scale. Obfuscation is encryption that is thoroughly broken to where many people pretty much know how to break it. Things that are not commonly easily broken are called encryption. That's sort of where it is. And that line, of course, changes as the time passes. So the Caesar cipher was military-grade encryption 2,500 years ago. You take each letter and just move it forward a couple in the alphabet. So this readable string turns into this unreadable string, and that was sufficient to protect military orders from unauthorized reading at a time when almost nobody could read at all. So even a small scrambling of the text was enough to render it effectively unreadable. Of course, it's no longer secure by any means, but it will mean that a simple strings command like we've been using, or bin text, will create unreadable output, and that might be enough. XOR is another common one. You can take any kind of binary data and just XOR it with another. So you take the original data and XOR it. See, it looks like I can line that up better. There, take your original data, you do it bit by bit. So you have data and you have the key. And so 0 XOR 0 is 0, and 1 XOR 1 is 0. If the two inputs are the same, you get 0. If they're different, you get 1. This, by the way, is used instead of and or because it is not information destructive. If you feed in data that is half zeros and half ones, and your key is half 0 and half ones, the output will be half 0 and half ones. If you were to use and or, then 3 of these outputs would be the same. So an input that was 50% ones and 50% zeros would turn into something that was 3/4 ones and only 1/4 zeros. And we'll get here a little later, but the Shannon entropy measures the amount of information in a bit stream. And that is called an information destroying transformation. If you feed in something that's half ones and half zeros, that is rich in information. Something with 3/4 ones and only 1/4 zeros has less information in it. And what that means is you cannot reverse it. You destroy information with that kind of transformation. If you don't want to destroy information, you have to have this kind of transformation where half of it is 1 and half of it is 0. So you preserve all the information and you can get back. That's why you use this exclusive OR. You could just as well use exclusive AND, but you can't use OR or AND because they destroy information. So if you do this, if you XOR it with the key, you can XOR it again with the same key and you'll get right back where you started. Because another way to read this is when you feed in the data and then you feed in the key. And if the key is 0, you don't change the data. And if the key is 1, you do change the data. So if you XOR it again with the same key, you'll take the ones that changed and change them back. And the ones that did not change, you will leave unchanged. So it's a very simple transformation, but it does make things very different. So if I encode high with a key of 3C, then the high is 4849, and that's this 8 bits and those 8 bits, and this is 3C. So you're going to get these results, just totally different data coming out. It scrambles it very well. So attack at noon with spaces in it turns into this garbage, curly braces and H's and delete keys and forward space keys, just completely garbled stuff, which is the point. Nobody's going to be able to read that easily, but it is very easy to reverse it in your code. So, and you reverse it the same way you create it, just run it through the key again, you'll get back where you started. So you can easily detect single byte XOR encoding, of course, and reverse it because the total number of keys is only 256. So you can just try all 256 keys and see which one looks like readable text or whatever you're hoping to get. You can, of course, encrypt any kind of data this way. So here is XOR encoded executable file. It starts with _H, but a real executable always starts with MZ. So if you have even one character that you can deduce the key. And so if you just try all these and look at the first couple of bytes, then you'll see this is 4D5A, which is MZ. And so you can try them until you find it, or you can, of course, mathematically deduce the key too. And so when you decrypt it, you get MZ. And then you get this stuff down here. This program must be run on Windows, not on DOS, something like that is at the start of every executable file. Notice that a whole lot of a file is full of zeros. This is true of almost every file format. Something that is not compressed or encrypted typically has a lot of padding in it because you have a field reserved for some purpose and a field reserved for another purpose, and you don't really fill it up. So you have these 0 bytes all over the place. That means, in fact, it's very easy to detect XOR encryption. And by the way, there's a lot of people that have written tools in Python and other languages, including Lenny Zeltser, to help you reverse XOR. But anyway, you can just look for a common string like that text. This program would be in there somewhere, and try keys until you find it. But notice, here's that same thing, that executable file. And this is the MZ. And notice all these 12s, all the zeros. If you XOR 0, it turns into the key, because all the bits of the key that are 1 flip to 1, and all the bits of the key that are 0 remain 0. So you'll see these 12s all over the place. So it's actually extremely easy to find the key. The key is what all these 12s are. So that's why, in fact, if you don't want your XOR to be blindingly obvious, you often do no preserving XOR. So the rule is use XOR encoding, except if the plain text is null or the key itself, leave it alone. And that is not simple XOR, but it does work, and it also reverses itself. So now, instead of getting this as your encoded file, you get this. The zeros are all over the place, unchanged, but the rest of it is no longer readable, so you can't read the strings. Anyway, that's what you might see. And remember, this is often the case. There's no particular reason for the malware author to be mathematically pure or use a simple encoding. They use whatever works, whatever's fast to encode, and you aren't going to get caught. So you can spot these things in the assembly code. You'll see this XOR function someplace. So here's the code that does that. It sets up some kind of loop, and then it does XOR with a fixed constant value. So you can find where XOR is in the code and find occurrences. And of course, there are some innocent uses of XOR, but you can try to spot the ones that look suspicious. One thing that's extremely common is XOR something with itself. That is the cheapest, fastest way to load 0 into here. If you write in C code A equals 0, it will compile down to an XOR like this, because it just is what compilers like to create. So this is not suspicious at all. If you XOR a registry with a constant, then that's more likely to be an encoding scheme, because it is pretty strange to have a legitimate reason to XOR with just a fixed constant. Is not something you would normally do. XOR a memory reference with a different memory reference might be an encoding loop with some kind of more complicated than a single byte key or something, or it could be actually deliberate. So here's another example, a single byte XOR loop. Here it is doing XOR EAX with EAX. This one is the innocent one that just puts a 0 in there. Here's the one that XORs EAX with 12 hex. And so here you've got the loop. Well, I'm not really seeing the loop. Jump short low 412F4. Move counter. Yeah, here's the loop. Okay, so it goes up here. So this is the loop. And here it is going through these things and XORing the bytes one by one. All right, you could just as easily use any other transformation. You could just add one to the bytes. That would be like the Caesar cipher, where you just move them forward. You can rotate them left and right, where you rotate the bits, like doubling each of the value of the bits, and then take the one on the end and wrap it around. You can, there's also this term called rot 13. It's moving things forward 13 letters in the alphabet, which would affect only readable text. This would affect the whole 8-bit byte. You can use multiple bytes for the key in any of these algorithms, or use chained or loopbacks, where you actually use a fixed key for the first byte, and then you use the encrypted byte as the key for the next byte. These are all ways to do it that are just a few commands in assembly code and don't require storing anything, that makes it easy for the analyst to understand what you're doing. And another one is, of course, base64. The original purpose of base64 was to email binary data. Email is ASCII only data because it's really, really old. In the early days, networks were slow and very unreliable, so they had to put error checking in every byte. So you'd have even or odd parity, which meant the total number of ones in every byte had to be even or odd. So the highest order bit was not used to transmit data. It was used to achieve even or odd parity. So the ASCII character set only used 127 possible characters. And that meant you could not move binary data in ASCII. You could only use 7 bits in each byte. So in order to move binary data, they developed this base64 encoding, where you use the uppercase letters, the lowercase letters, numbers, and then a couple of punctuation marks. They give you a total of 64 characters. And now with one character, you can encode 6 bits instead of 8. So if you have a binary message, it will just turn into this kind of stuff. No spaces, upper and lowercase, numbers, and some punctuation marks. That's encoding with base64. And you can turn things into that. If you have ATT here, these are encoded as ASCII with 8 bits for each character. And you write them down that way and then group them in 6 bits at a time. So this is 1, 2, 4, 8, 16. So it's the 16th letter, which is Q. This one is the 21st letter and so on. So this 3-letter message in ASCII encodes as this 4-letter message in base64. And it's not encryption. It makes it so you can't read it, but it is easy and trivial to reverse it back. But it will stop people from recognizing strings. It might. And so you can go online and have websites that will do base64 encoding and reversing, and you can do it in Python and any other way. It's, of course, very commonly done all over the place. But if you don't know that, then it hides strings from people. By the way, you can worry, what if you only had 2 letters? Then you'd have 16 bits. And when you break it up into groups of 6, you'd have 2 groups of 6, but only half of the last group. So you have to have some convention of how to express that. And which one of the conventions is to add an equal sign to the end if you're missing one of the input characters you should have, or maybe 2 equal signs if you're missing 2 of them. That's one of the ways to encode that. It's a rather strange system, because just from the length of the number of characters, you could deduce this. You don't really need it. But anyway, that is part of the original specification from decades ago used to put binary data in email, and most base64 implementations do require it. So you'll see things like this. This is malware. phoning home. So it does a get for a web page, index.htm, but this is obviously not a real folder name. This is a base64 encoded string. So in a HTTP request, you have data encrypted, which will be things like your stolen data leaving the network, botnet command and control data telling the network that you are under control, and things about the slave that's here. So here you have data, and also you can put it in the cookie. That's one way to move obfuscated data out of the network. So if you decode that cookie, you'll see that it turns into bot 54164, the kind of thing you would be sending back to the command and control center that'll have a control panel that says, I've infected 10,000 machines and here they are. And these many are Windows 95 and these many are Windows XP or whatever they are. And then you can send commands to them and use them to do a DDoS attack or something. So if you want to spot malware that uses base64, you'll typically just find this string in there. This is the easiest way to do it. You define this string, then you take the input data, turn it into binary, turn it into 6 bits, find out how many, and then go that many spaces through this string to find it. So typically you'll see this. And by the way, you can put a different modified base64 string where you put the letters out of order or something. So it's not standard base64, but it still uses the same kind of logic. So here they just take the lowercase a and put it here, and that changes a lot of the letters. So now the scrambled base64 looking stuff will not reverse on a normal website because it's not exactly standard base64. All right, and of course you can decode it using a custom indexing string by writing that in Python or any other language that is handy. So let's take a look at some Cahoots. 13A is here. Right. Ah, there we go. Good. If you win, I'll have to figure out who that is. Anyway, all right, so let's go. All right, what coding reverses itself when you perform it a second time? Okay, that's XOR, good. All right, which one is easily reversed? All of them? These are all obfuscation, not encryption. You can easily reverse any of them if you, without a lot of work. None of them really hide data from a serious attempt to get in. They just make it a little bit difficult. All right, which one uses letters, numbers, plus, and slash? that's base 64, so you have 64 characters. All right. Good. All right, and which one turns 3 bytes into 4 characters? That's base 64. Your message gets longer. All right. I think I know who those people are. All right. So let's go back to here. All right. So then you could use real cryptography, of course. If you're not messing around, you use something like AES or DES or RSA or something like that. You can really encrypt network traffic with SSL. That's what you do if you really don't want people getting in. The problem is those encryption routines are kind of big and obvious. So if you're using the system Microsoft API encryption routines, it'll be easy to spot that. If you write your own code, it will have standard constants that are used in the matrices and stuff. So, you know, and of course, if you do symmetric encryption, then you have a key and you have to hide the key somewhere. This is why I'm always giving Android apps trouble, because about half of them encrypt stuff in symmetric encryption and then try to hide the key on the phone, which is futile. But so anyway, it is an issue with this kind of encryption, and that's why it's not that common to really use it, but you can. So if you're using OpenSSL libraries, then you'll find these comments that are in the OpenSSL package. So it'll be pretty easy to spot unless you modify the library. And if you call the Microsoft crypto functions, they're of course not hard to see. They have names like crypt encrypt, encrypt derived key, and so on, because Microsoft is not trying to make you confused. They try to give it a name that tells you what it is. So it will be pretty obvious that you're doing encryption and where to go to find the key and so on. You can also look for constants. Most cryptographic routines have particular constants you have to have in there, and so IDAPRO has a plugin just to look for the binary signatures of these. RC4 and IDEA don't have any magic constants. RC4 in particular is a very entertaining encryption scheme that was very popular for a long time. We talk about it in a cryptography class. It's really sort of like you shuffle the bytes like a deck of cards. So there is no magic constant, and it is really very clever. It turns out to have some serious security flaws, and it's now no longer recommended for anything. But for decades, we used it in everything because it is fast and simple and easy, and it looks like it's doing a great job, but it turns out that it's not doing that great a job. But for something like malware, you might be happy to use it. And so there's this thing called FindCrypt2 that you can run from a plugin. It will then tell you, I found some stuff used in DES in here. So they're apparently using DES, which was the US approved encryption routine until I think the 90s. It's no longer considered secure enough to use for banking, but it's certainly better than using the Caesar cipher or something in malware. And it's not that easy to crack without the key. So there's you can put a plugin in PEID, which is kind of funny. Most of these tools, you can add plugins. And so there's a plugin you can put in here that will then notice things. It found a base 64 table, and it found some Microsoft API calls calling things like crypt decrypt and crypt derived key. So, you know, there are extensions to our standard tools that will detect these encryption. And there's a general solution, which is Entropy. And I mentioned this before. This was one of the great things that Shannon figured out, how to measure the information contained in binary data and work with it, which is mathematically identical to figuring out the entropy, which is related to the temperature in physics. So what you do is you have 256 possible values of a byte, and you calculate the probability of it having a certain byte, and then you add the probability times the log of the probability for every byte. And what that means is, if it is completely random and every value is equally likely, then you get an answer of 8, which is the information content. Completely random bits have 8 bits of information per byte, which means there's no air in it. You can't squeeze it down. You can't compress it any smaller. But if you have something like this file we looked at back here, way back towards the beginning. Yeah, this file right here. It has all these zeros. Obviously, you could just squeeze those zeros down. You could take this whole string of zeros and you could encode it as just 25 times 0. So I only really need 2 bytes to encode this whole block of data. And something like a Microsoft Word document is all full of this stuff. So this does not contain 8 bits of information per byte. It has less information than that. It can be compressed and made smaller. And if you do, then you'll have more bits that are used in each byte. And that's what Shannon information is. It's a measure of how much actual information is included in the data. And therefore, you can calculate this. You can take any region of a file and then calculate this mathematical entity. So here's something I did a while ago as a demo. I put in random data. So first I put in 10,000 random characters, and then I put in base 64 encoded, base 32 encoded, and base 16 encoded versions, and then just 10,000 characters that are all just capital A. And you can calculate the entropy with binwalk, which is intended to analyze the firmware of IoT devices. We use it for a lot of purposes. So this is completely random data. It's maximum entropy, which this interprets as 1. In the units we're using for this class and for usually using malware, we call that 8. This is completely random, 8 bits per byte, or close to it. This is 6 bits per byte because they're only, base 64 only has 64 possible values, and the rest are never used. So obviously only 6 bits contain information in each byte. Here's base 32 and base 16 that only contains 4 bits per byte. And here's the 10,000 characters that are all just capital A. The entropy is 0. That contains essentially no information. All 10,000 bytes really contain just 1 byte of data. It's an A, which is essentially 0 bits per byte. All of it is just wasted, and it could be compressed down to a much smaller size. So that's what entropy is. And the reason it's useful is because now you can scan an unknown file. So here I made a file with bitmap image, and then a GIF image, and then a JPEG image. And bitmaps are not compressed at all, so they're low entropy. GIFs are compressed, but not very efficiently. JPEGs are efficiently compressed, so the entropy is almost maximum. They've squeezed all the air out and made that file as small as it can get. So now you can search for high entropy content. There's an IDA Pro entropy plugin, and it can calculate the numerical entropy of each section. So here's the text section, which contains assembly language, and that entropy is 6 bits per byte. It's like base 64. It doesn't explore every possible value, but it's pretty close to random. Here's a data section with an entropy below 1, and another data section with an entropy of 5. It probably contains images, and another data section with an entropy of 1.3. So you can see that the different areas do have different entropies, giving you a clue what's stored in there. So here's the recommended parameters for this are to take 64 bytes at a time to make chunks and then calculate the entropy there. And so base 64 encoded stuff will have an entropy near 6. Areas that are random because they're encrypted or compressed will have an entropy up near 8. And you can plot a graph in IDA Pro. So you'll see the color changes. So the really white stuff is high entropy, like 7. The dark stuff is low entropy, like 0. So you can find what areas appear to be interesting here. So this area is high entropy, this is low entropy, this stuff is middle, and so you could figure out what area to examine. And you can graph it like this. So here they show you the interpretation. This is assembly code. So the entropy is about 5.4. It's not really completely random, but it doesn't explore all possible values because assembly code pretty much has the same thing over and over, like move and move and or and jump and stuff. It pretty much repeats itself a lot. It's not completely random. Here's constants. They're just effectively random. Here's an encrypted configuration area. Here's more low entropy, you know, so it might be one way to find interesting areas to look at. All right, and then there's just custom encoding. You could make up your own scheme. This happens a lot in the world of cryptography. A lot of people, especially at companies, they will just make up an encryption scheme and then sell their product. This is a really, really, really bad idea, because anything you think of that you think you're clever almost invariably turns out to be something that some cryptographer thought of 300 years ago, and it's been cracked. you should never make your own encryption. Just use the normal stuff like AES and ECC and RSA. That stuff has been carefully examined by top-notch mathematicians for decades until they really have made sure that there's nothing seriously wrong with it. And anything you thought up, like I'll just shift everything one to the left and flip the third bit and then switch the third and fourth byte of every block of 6 bytes, they'll never get there. It turns out all these things are trivial to crack, even if they sound pretty clever. And there are a lot of commercial products that do stupid things like that. There are a lot of Android apps that do stupid things. I've seen them. Stitcher, something like the number 10 most popular Android app. Stitcher used the Caesar cipher to encrypt passwords. And I sent him a vulnerability report and said, dude, you're sending Caesar cipher encrypted passwords over the internet. Why don't you use HTTPS? And they said, what's HTTPS? I said, man, this is not good. Anyway, now they're using HTTPS. But there's an incredible number of developers that are incredibly innocent, like babes in the woods about encryption. Anyway, so however, for malware, it makes perfect sense. Do something just a little bit off the map, like XOR and then base 64, or just scramble it in any way you like. There are, by the way, hundreds of old lame encryption routines like A4 and stuff that were used in products and then proven to be unsafe. And the code is still just sitting around. So you could use it as long as you don't really need cryptographic security. So the easiest way to reverse custom encoding, here's some kind of encrypted file. It just looks like random stuff. So you can find create file and write file. So it's writing files with this in here. It's using XOR with a pseudo-random stream, which, by the way, is essentially what all encryption is. The only trick is how perfectly do they make that pseudo-random stream. And so you have some encrypted write here, number of bytes to write and the handle to the file. So now it's going to write stuff. And so if you have custom encoding, this is great for the attacker, right? The point is to confuse the analyst, and the analyst is not going to be able to use any pre-designed tool on it. There's a Mandiant tool to find strings that will try to find obfuscated strings, but of course it can't find a custom encoding. It can only try the normal stuff like base 64. So if you want to decode this, you could look at the assembly code, figure out exactly what it does, and then write your own code in C or Python or something to reverse it, and that would work. But that's the hard way. The easy way is to just find the part of the code that decodes it and put a break in there. Somewhere in the malware, it has to decode that stuff. So use their custom decoder to decode their stuff. I do this all the time at PHP malware. The only problem is always work in a disposable virtual machine, because I've done it with PHP malware, and I often have made a mistake finding the spot where to put the break in. So it decodes it, and then I let it do some of the malicious stuff before it hits my breakpoint. So it does some damage to my machine. So, be aware of that. Anytime you're running malware at all, or really examining malware at all, you should be in a virtual disposable system, because it is very easy to accidentally let it do some of its malicious stuff. But anyway, that's the point. You don't really need to figure out how the decoding works. You just need to spot where it is and break it and look at the contents of memory after the decoder runs, and you may find the strings you're looking for. Remember, of course, the fundamental principle from the very first lecture. You don't really need to figure out everything about the malware. You're just trying to answer a few basic questions. I want some indicators of compromise. I want to know perhaps how to clean it off, things like that. So I don't really need to find every fact about the malware. Just like a detective investigating a crime does not need to find every clue. You just need to find enough of the clues to get to your goal. So anyway, so you can try manual decoding. Here they're writing a Python script to do null preserving XOR, and here's a base 64 decode where they're going to use, I think, a custom string and so on. You can make a custom string here. You can use the standard base 64 and then just have the custom string here, and wherever you found this character, you just look up this corresponding character in the other string. So it's very easy to take the standard base 64 and turn it into a custom base 64 to match the string you find by just looking at strings in the code. So, that's one way to go. In the book, they say use PyCrypto. We founded the cryptography class. PyCrypto has gone out of fashion. The cool thing now is PyCrypto Dome, which does the same thing, but it seems to run better in Python 3. So anyway. So here's what you do using malware. You set up the malware in your debugger, get everything ready to go, and then you run the malware and you put a breakpoint after it writes the decrypted thing. You know, you modify the code or put a breakpoint in so it doesn't erase it after decrypting it, which is what it would probably do normally. And so here's a decryption script. You can do this in some of the projects I had people doing this. You can write Python, which will then open the file and then run the malware and even run the debugger from inside Python. You can do it all with Python controlling it if you like. It might be necessary for complicated situations, and you have that one project where you have 256 files to run and find the keys in, where you do this kind of thing. You run it from inside Python. That's one way to get there. Anyway, there are many ways to do it. Let's try these cahoots. Good. Yeah, Chaz, the basic decoder gets you to a normal character, and then you just look for the corresponding character in the custom alphabet. That's how you do it. Anyway, let's see how this works. All right, so what's so weak, it's not even considered encryption at all. Yeah, base 64 is just encoding. It's just a one-to-one transformation and can easily be reversed without a key or anything. All right. All right, which one uses names starting with CP? Microsoft Crypto API calls. All right. And what technique is commonly used in malware but difficult to find? Best Cipher 4, RC4. Pretty powerful, but not that great. All right, if you contain random bytes, what is the entropy? Eight bits of information per byte. That's what you call it. So that's a completely full file that is all in use and cannot be compressed any further. All right. All right. That's Taras and Horace. And Zoe. All right. All right. Stop recording and I'll post